So for alloy selection, we first considered going with something like the plain carbon steel like 1060 or a low alloy steel like 4340. Um, but a key concern with this project was that the sword blade being very long and thin would be prone to warping during heat treatment, which you can fix that afterwards, but it's just more difficult. Um, so to avoid this, we decided to use a 17-4 precipitation hardening stainless steel, and the precipitation hardening mechanism results in much less residual stress than a traditional quench and temper. So as a result, there was essentially no risk of the blades warping during heat treatment. This alloy is also very tough, so the sword should be able to withstand abuse without fracturing. However, the trade-off is that this alloy does not get quite as hard as as more like traditional quenched and tempered carbon steel, but it still does achieve a reasonably high hardness that is in line with historical examples. And so we chose to use the investment casting process to cast this sword. This is because investment casting has excellent dimensional stability and surface finish, which allowed us to cast this long, thin sword very close to its final dimensions, cutting down on the amount of post-processing that we would have to do. This process began by 3D printing 4 sword blades. They were printed out of pure PLA, and each blade was printed in 4 separate pieces, which were then glued together. And then the 3D printed swords were attached to a wax gating system. That gating system was coated in multiple coats of a ceramic slurry, and then the wax and PLA were burned out to create the mold. And then during casting, the metal is just poured in. And all of the castings came out reasonably well and could have produced usable swords. However, some of them, the tips didn't fill completely, and others had some minor ceramic inclusions in the tang, but one of them came out perfectly, and this one was used to make the final product. And then for heat treatment, there were 2 stages. First was a solution anneal, so it was heated to about 1900 degrees Fahrenheit for about 30 minutes, and then quenched to room temperature. And this forms a low-strength martensite structure that's supersaturated with copper. And then afterwards, the swords were aged at 900 degrees Fahrenheit for 1 hour, and this precipitated its copper-rich phase from the supersaturated matrix, strengthening the alloy. Let's see, most of the post-processing involved just grinding, cleaning up the blade on a belt grinder and grinding in the bevels. There wasn't a whole lot of grinding that needed to be done, just because we were able to cast the sword so close to its final dimensions. And then the handle of the sword consisted of a hidden through tang that was peened over the back of the pommel to produce a mechanical connection. And then the pieces were also epoxied in place to fill in any gaps and provide a secondary form of connection. The crossguard and the pommel were hand forged out of mild steel, and the handle was carved out of white ash. And it's kind of neat that with the original silver line-headed Kato, the blade would have been forged while the guard and the tang were probably cast, but with our sword it's the other way around. The blade is cast and the guard and tang are forged.